Welcome to today's episode, MDU Platypus Galaxies. When the James Webb Space Telescope recently pointed its mirrors toward the deep universe, it found a class of celestial objects that directly contradict our established timelines for cosmic evolution. Astronomers have identified exactly 9 of these objects. They are calling them Platypus Galaxies, named for their unusual morphology, a central elliptical bulge fused with spiral arms, wrapped inside a highly distinct dual-ring structure. Galaxies are highly structured. We sort them into distinct categories like spiral, elliptical, and irregular. A platypus galaxy possesses traits from all of them at once. The metrics are extreme. These structures carry up to 10 billion solar masses of gas, feature massive central black holes, and generate intense, rapid star formation. But the real issue is their age. They appear fully formed a mere 1 to 2 billion years after the Big Bang. Standard theories struggle to explain how these features could exist simultaneously that early in the timeline. Cold dark matter frameworks, hierarchical clustering, and monolithic collapse models generally fail to account for such complex geometry stabilizing in such a short window. This gap in our understanding suggests we need a different approach. To see how a platypus galaxy forms, we have to look past standard assumptions and test a model based on the Cosmic Helium Evolution Theory, or CHET. We start by initializing an empty digital void with a single gas cloud containing 10 billion solar masses. The CHET framework suggests helium-4 dictates a galaxy's shape. We inject our cloud with a baseline helium-4 ratio of 24%, matching the cosmic average. That specific helium density immediately affects stellar evolution. The first stars that condense from this cloud are highly massive, burning incredibly bright and exhausting their fuel in a fraction of the normal time frame. Because their lifespans are so short, these massive stars quickly collapse. This triggers a chain reaction of rapid gas accretion, pulling surrounding material inward to forge a supermassive black hole at the center. At this stage, the model correctly predicts the central bulge and starburst activity, but without a significant increase in mass, the outer structure is unstable. In our simulation, the gas simply drifts away, failing to hold the ring shape seen in our deep space observations. To stabilize the structure, we apply the hidden neutrino theorem. These neutrinos embed themselves within normal matter's empty spaces. Once locked into place, their binding energy increases the host particle's mass by 20 times, providing the needed gravitational scaffolding. With the inclusion of hidden neutrinos, the simulation stabilizes. The orbital velocities now align with the rotation curves measured in the 9 identified platypus galaxies, allowing the outer gas to maintain its orbit. To further refine the model's accuracy, we have to layer in the final physical variables, starting with electromagnetism. By modeling the electromagnetic force generated by the central supermassive black hole, the simulation begins to capture the specific density and luminosity gradients observed in the galaxy's immediate environment. The final variable is viscosity. To match the platypus morphology, we calibrate 3 metrics to low levels. Dynamic viscosity requires 0.0012 Pascal seconds to allow gas rotation. Setting kinematic and bulk viscosities near 0 allows massive gas clouds to condense. The physical results of these low-resistant fluid dynamics are immediate. The chaotic gas and dust are forced into the path of least resistance, settling into the signature geometry of the platypus anomaly. The result is a stable system featuring rapid stellar ignition, a supermassive core, and the distinct ring-like structure. When these fluid dynamics are combined with helium-4 density and hidden neutrino mass, the simulation resolves every major morphological feature of the platypus system, from the ring spacing to the central bulge. When we place the final output of the simulation next to the optical data pulled by the James Webb Space Telescope, the resulting model produces a structural match that reflects the primary features identified in the data. This demonstrates that a complex, early universe galaxy can be modeled without relying on the cold dark matter paradigm. By treating helium-4 and embedded hidden neutrinos as the primary drivers of gravity and mass, the structures in our cosmos align with a functional, predictive framework. Researchers can now use the CHET framework to calculate the data we expect to receive from next-generation installations, like the Square Kilometre Array. These redefined physical laws will also assist the Large Synoptic Survey Telescope as it categorizes the billions of galaxies it maps, refining how we measure the deep cosmos. If you want to explore the theories shaping our universe, return to the MDU channel for more deep dives into the mechanics of reality. Like, subscribe, and keep looking up.